Welcome back to MLT 115. This is part 2 for the Graphs and Standard Curves lecture. In this part of the lecture, we'll be talking more about blanks, standards, and getting more into what a standard curve is. So there's certain things that we have to do to prepare instruments to run patient samples. And one of those things that we do is to run a blank samples. Blanks are reaction mixtures minus the substance being tested or the sample being tested. So usually we have a concentration, or the blanks have a concentration of 0, and they are usually ran first before a sample. So let's talk about two different types of blanks. We have a reagent blank and we have a specialized blank. A reagent blank is measuring the instrument as it is set to 0 on the blank. We have all components of the solution in the blank except for the substance that we're trying to measure. In a specialized blank, the instrument is set to 0 on a sample of water or even maybe an empty cuvette. Remember, the cuvette is the little sample container. Some we just use water, some we use distilled water as our blank, or again just the empty cuvette. So like I said before, we usually run blanks before we run our patient samples. With reagent blanks, you simply just run your blank and then you're able to run your patient samples. There's no additional mathematics involved to be able to get your sample concentration. But with some specialized blanks, you may have to subtract the blank reading from the sample reading to get the true concentration of the sample. And this is due to some of the background that can be in those specialized blank samples. So now let's look at some examples where blanks had to be subtracted from the samples in order to get the true concentration. Let's look at our blank here. Our blank absorbance was 0.1 and our standard was 0.6. Our standard for this example is like our sample. So in this example, we're going to have to subtract our 0.1, which is our background from our blank, from our 0.6, which is our sample or our standard. So that's what they've done here. Our 0.6 minus 0.1 is 0.5. So this would be the adjusted absorbance reading, taking account for that background of our specialized blank. Next up, we have controls. Controls are a lot of times either positive or negative, or sometimes you have different levels of controls. Maybe you have a low, medium, high, but there's different reference standards for controls, but they're usually solutions of a known value or a known range. And we run controls with patient samples to monitor our method of performance. And they may be used in more than one concentration, like I was saying. They may be a high, medium, low, or like I said, it may be either just a positive or negative control. And again, we're doing these, we run controls with our samples to make sure our methodology, our testing methodology is good and that we're putting out quality patient results. It's all part of our quality control program. Next up on this slide, we have some more terms that we need to be aware of for the laboratory. We have things called reference standards. These are usually solutions that are used to help validate or test the method and design of our instruments or our testing methods. And our reference standards are usually of known concentrations. So if we run a reference standard, we know what that reference standard should read out as. So if we run a reference standard and it doesn't come out exactly what we think it should be or know it should be, then there's probably something wrong with our instrumentation. Calibrators, we use calibrators to calibrate or adjust our instrumentation to help dial it in, make it more accurate. We use our calibrators to help calibrate our instruments ever so often. Maybe we calibrate weekly, maybe we calibrate monthly, maybe we calibrate quarterly. But the calibrators are very important in that whole process of making sure that our instruments are adjusted and dialed in exactly right in order to be able to put out quality patient results. Our working standards are used to establish instrument response to solute concentrations. These are similar to our reference standards, or sometimes those can kind of be used interchangeably. But these are standards, again, these would be of known concentrations, or they would be a different set. It could be a set of standards, and each standard would be of a different concentration, but it would be a known concentration. So if you run the whole set, like you have a set of 5 working standards, each standard would be of a different level. Say maybe you have a level 1, level 2, all the way up to a level 5. And each level would be increasing in concentration. And again, that's another way to test and establish your instrument, make sure everything's running correctly. A stock standard would be a highly concentrated solution of pure substances. So that's the key, pure substances. And you can make your working standards from your pure stock standard solutions. So maybe when you're ordering in a lab, you can order stock standards, and then you can make the actual working standards that you're going to use with your instrumentation from your pure stock standards. Usually the methodology to make those working standards from those stock standards is to dilute it down. And again, if you need a set of different concentrations for your working standards, say you need a low level, medium level, high level, or a set of maybe 1 to 5 like I was just talking about, you would dilute it down to whatever concentration you would need or whatever range you would need. And then you could use those working standards to actually test your instrument or set up your instrument. It's necessary to know how to work some word problems that involves our working standards. So let's look at a word problem that's associated with our working standards. It says prepare 100 milliliters of a 0.2 milligrams per milliliter working standard from a 10 milligrams per milliliter stock standard. And first thing we need to do is find the dilution factor. So we're going to be looking for X. So we've got to take the information that it was given, and we've got to figure out our answer. So again, I like to underline my information. So we're going to be preparing from a 10 milligrams per milliliter stock standard. So we're taking that stock standard and making a working standard. Okay. They also give us the 0.2 milligrams per milliliter. That's what we're wanting to get to. So this should look familiar to you. We're going to end up doing some cross multiplication here at the end. So I'm going to actually cover the answer up with a box just so I can write on top of it so I can work my problem out. So we're going to set up our problem like this. Our 10 milligrams per milliliter times 1x equals 0.2 milligrams per milliliter. So we're solving for x. We got to have x by itself. So we need to divide this side by 10, this side by 10. So we're going to end up 1. X equals 0.2 over 10. Now we can do cross multiplication. 0.2x equals 1 times 10 is 10. And again, we're trying to get x by itself. 0.2 to solve for x divided by 0.2. So x is 50. So that's our final answer. Let's look at another example. Dilute the 10 milligrams per milliliter stock standard 1/50th to prepare the working standard. Use ratio and proportion to find the volume of the stock standard required to make 100 milliliters working standard. So how are we going to set that up? First thing to know, it says use ratio and proportion. So we probably know we're going to do cross multiplication, and it tells us 1/50th, and it gives us 10 milligrams per milliliter. Let's see, what else do we need to know? And we need 100 milliliters of the working standard. So we're going to use that information to set up our problem. And it says we're going to be finding the volume of our stock standard. So that's what we're looking for. So we're looking for volume, so we're most likely going to be looking for milliliters. It already gives us our first half of our ratio, which I'm going to write it over here, 1/50th. And then the other half would be our milliliters. We're trying to get 100 milliliters of our working standard, and we're trying to solve for our unknown, which we're going to put as x, and again that's going to be milliliters. So at this point we can do our cross multiplication. So 100 times 1 is 100, and then 50 times x would be 50x, and then we divide both sides by 50 to get x by itself. So 100 divided by 50 would be 2, so x equals 2, and that's the answer that we've got here on this slide. So now we need to define exactly what a standard curve is. A standard curve is a graph of known values, and we're going to look at a sample or an example of what a standard curve looks like on the next slide. But it's used when a substance do not obey the formula, such as Beer's law. If a substance doesn't follow Beer's law, a standard curve might be a tool used to determine if a substance does obey a formula or a pattern. This is our example of what a standard curve looks like here on the right hand side of the slide. So this is our graph, and along the bottom on the x-axis it's showing concentration, and on the y-axis along the side we're doing the instrument readout. And all along the observed line is your standard curve, the points along your standard curve. And the two columns in the chart gives you your concentration and your instrument reading that are your points for your standard curve. So the very first point, or the observed line, again this is your standard curve, and you got to have 3 points to establish a line or to make a line, but each one of your points along your standard curve, the very first one is at your origin, or your 0 for your y and 0 for your x. The next one, your next point along your standard curve, is at the 1 concentration and at 0.67, so that's right here. And the next one is at 5 concentration and 0.833, and so on along your standard curve or your observed line. So you've made a pattern to complete or establish a line. So this line or standard curve does not follow Beer's law. You can see Beer's law down below, so it's not following that pattern. When we're plotting out our standard curve, again, we have to have at least 3 points or 3 concentrations in order to establish or to make a line. The concentrations must cover the range of expected sample concentrations. The working standards have to be of significant concentration, so they have to cover within a certain range that you're working within. Also, your standard concentrations need to be in the appropriate unit of measurement, and the units must be in the correct graphing system when you're working with standard curves. When you're plotting or establishing a standard curve at the beginning, you want to use the appropriate working standard concentrations. Again, you've got to have enough standards to establish a line. So you have to have at least 3 standards, right? Because we have to have 3 points to even create a line or a curve. And then you're going to dilute the working standards, and they can be serial or independent dilutions. Again, so you might be making up your working standards, or they may come pre-made, and you can order them already diluted down to the concentration that you need. So once you have established the working standards that you need and the concentrations that you need, and you prepared those working standards, then you can finally run those standards or dilutions on your instrument. So you can actually get a readout from your instrumentation, so you can establish your standard curve and plot it out on your graph. So let's say we went through all that work of plotting and coming up with our standard curve. This graph has 5 points on it of different working standards, and a standard curve was established. Well, you could really even say 6, because we could say our origin is the first coordinates on our standard curve. But along the bottom, you've got your concentration, and along the side, you have your instrument readout. So you have a standard curve now with a blank at concentration 0, and again, that's at our origin, 0, 0. And then our first standard is right here. Oh, let me fix that. Our first standard 1 is going to be at concentration 100. Our standard 2 is going to be at 200. Standard 3 is going to be at 300. Standard 4 is going to be at 400. And our standard 5 is going to be at 500. So now that we have all of our standards ran on our instrumentation and readouts for each of our standards, we have established our standard curve, which is the whole line. So what's the whole point of establishing this standard curve. Why go through all this work to come up with this standard curve? Well, let's say we have a sample and a patient sample, and we run it on our instrumentation, and we have a readout of absorbance. Okay, that's our instrument readout, and our absorbance is 0.4. Okay, but we need the concentration. We need to know how much of that substance is actually in that sample. Say how much of that substance we're testing for. What is the concentration in that sample? So, in order to figure that out, we have established this standard curve. So if our readout is 0.4, then guess what we can do? We can go over from 0.4 on the y-axis and draw us a line over to our standard curve, and then go straight down to our x-axis to where it hits to figure out the concentration. And I'm sorry, that's not perfectly straight, but we can get the concentration of our sample because we have established our standard curve. So our concentration of our sample, let's just say it's 275 milligrams per deciliter. Okay, so that's our concentration of the sample. So that's why we establish these standard curves, so we can ultimately find out the concentration of our patient samples. So in interpretation of standard curves, if a graph reveals previously defined relationships, such as Beer's law, that's great. But sometimes things don't follow Beer's law, and we need to establish and create a new standard curve so we can reveal new previously not defined relationships. And we may have to use the graph or derive a formula such as our slope. And we learned how to do slope in part 1 of this lecture to be able to come up with our standard curve, to be able to ultimately reveal the concentrations of substances in a patient sample. Sometimes there's no relationship between the concentration and the instrument readouts. So in those cases, alternate protocols or instrumentation methods must be used. I hope you've learned a lot in part 2 of this lecture. If you have any questions or any concerns, please don't hesitate to reach out to me through email or come see me during my office hours.